Okay, in this screencast we're going to look at all sorts of numbers related to atomic bookkeeping. These all have to do with the relative numbers of protons, neutrons, and electrons in an atom. We'll look at atomic number, we'll look at mass number, we'll look at isotopes, we'll look at ions, both cations and anions. We'll look at the average atomic mass of an atom. We'll predict which atoms might be unstable based on the band of stability, and how they like to add or electrons based on the idea that they like to have the same number of electrons as those of a noble gas. This is Screencast 4.6. Okay, atomic number. What does that mean? Well, it simply means the number of protons. In our class, it's the blue number on the periodic table, and this means that we define what an element is based on the number of protons it has. It's a nice system since they tend to go up, sequentially. If you have 2 protons, it's helium. It tends to show up down here, for example. This is the atomic number. This cannot be. Sulfur never has 32 protons. It only has 16. If you have a periodic table out during this screencast, you'll find it handy. Mass number is defined as the number of protons and the number of neutrons. So, for example, that number right there is the mass number. It's that particular atom of helium which has 2 protons, which it must, and in this case, 3 neutrons. See how 2 plus 3 will equal 5? Notice how the number of neutrons is hiding within that. 5 minus 2 equals 3. Therefore, helium-5 has 2 protons as it must, and in this case 3 neutrons. So, that means mass number usually shows up here, but you might see it also written with a dash like this. An isotope is based on that important concept that for an element, the number of neutrons can vary within a given pile of atoms in a nice fixed ratio. So, say you got a pile of helium atoms. They're not all helium-4. Some of them are going to be helium-5. This one has 2 neutrons, this one has 3. Isotopes are atoms of the same element where the number of neutrons varies. Within a given atom, you can also have varying numbers of electrons. The electrons can come and go. They don't change the identity of the element, but they give it a charge. If it's not equal to the number of electrons, it can either be positive or negative charge. Here's one with a positive charge. Sodium plus 1. Well, sodium's got to have 11 protons, otherwise it's not sodium. Plus 1, it looks like add an electron, but no. Electrons have a negative charge, so always compare the positive charge to the negative charge. To make this thing overall plus 1, you need to remove a negative charge. Why can't we remove a positive charge? Well, that makes it neon. That makes it a different element. The number of protons has to be fixed to keep it the same element. Add or remove electrons to give it a positive or negative charge. When it has a positive charge, we call that a cation. Please don't pronounce it cation. This is a cation. The number of protons is greater than the number of electrons. For example, 20 protons and 18 electrons. That would be a dication. 2 more protons than electrons. If it's 20 protons, that's calcium. So this is the calcium dication. Anions would be the other case. The number of electrons is greater than the number of protons. And here's one where you got 3 more electrons than protons. 7 protons, look it up and you'll find that that is sodium. This is the, nitrogen. This is the nitrogen trianion. The average atomic mass, also known in our class as the red number, since that's what it shows up as on the periodic table, is that number under an element with all the decimal places. This is necessary due to the fact that you have isotopic mixtures for every element. So the mass has to be an average of those different isotopes. Fortunately, they're fixed. There's so many of them that it's a very precise ratio. Carbon, for example, 99% of it about is carbon-12, meaning 6 protons and 6 neutrons. But 1% of it has an extra neutron, and that's carbon-13. That means the average atomic mass will be very close to 12, but it'll be a little higher due to that 1% that is 13. To figure it out, just take the abundance of each one as a decimal and multiply it by that mass. Add up the next isotope and you should get a total. 0.989 of 12 is going to be 11.999 or so, and 1.1% expressed as a decimal point is 13. That's going to be a much lower number, but you add them up together, and there it is. 12.011 is the average atomic mass of carbon. Units are simply called atomic mass units. The band of stability is this cool concept that anytime you have too many neutrons in an atom, it's been observed to be unstable. Specifically, if it has more than 1.5 times as many neutrons as protons, that's generally been observed to be too many, and therefore it's outside of what they call the band of stability. Uranium-238, go ahead and calculate it and see if that one is stable or unstable. Well, uranium has to have 92 protons. The rest are neutrons. That comes up to 144. Divide it as such, neutrons over protons, and you'll see, too many. Better run away. This would be predicted to be an unfriendly atom. Finally, I'd like to at least briefly expose us to the concept of isoelectronicity. That is the idea that some elements prefer to gain or lose electrons based on what they need to become like a noble gas. Fluorine, anion, and neon both have 10 electrons. Neon, 10 protons, 10 electrons. Fluorine, 9 protons, 1 extra electron, so they both have 10 electrons. They are isoelectronic. Just to give you a hint into some later chemical reactions, fluorine loves to gain an electron to become like neon. Sodium loves to lose an electron to become like neon. Calcium loves to lose 2 electrons to become similar to the nearest noble gas, which is argon. And nitrogen, if it gains 3 electrons, becomes isoelectronic with neon as well. It's an extremely powerful predictor of chemical behavior. This is Screencast 4.6.